Great. Well, thanks everybody. So I'm going to be talking today about Omaha MUD's digital transformation using InfoWater Pro. And to give you a little bit of background, Omaha MUD stands for Metropolitan Utilities District. They're located in the Omaha, Nebraska greater metropolitan area. Water and gas service to about 600,000 people in the city. And just to give you a little bit of context, it's a pretty large system, so 3,000, that should be lineal miles, I think, of water mains, 11 pressure zones, 3 major zones. If you look over to the right here, it's zone 1, 2, and 3, and then there's some smaller subsidiary zones. So just a little bit of context here, because this will become important as we chat later on. Is the city really started out in zone 1 with 2 water treatment plants, which was by the Missouri River, and built some storage in zone 1. And then as the city systematically grew to the west, they started with a secondary zone 2 and then zone 3. These were, just because of topography, these were closed pressure zones. So we've got 2 very large closed pressure zones within this system, which presented some challenges that I'll chat about a little bit later on. So to give you an idea, there are about a total ADD, average day demand, of about 80 million gallons per day. 50 of that, so a large percentage of that is in this middle zone, this zone 2. So both in terms of demand and pure geographic area, we've got a very large closed pressure zone that again presents some challenges. So 3 water treatment plants, 6 storage reservoirs. There's really only 3 of those that are major storage reservoirs. The others are in some of the smaller zones, and they don't really significantly impact the system. So a total of 17 pump stations, and then within those pump stations, we had a total of 85 pumps, which again will become important as I talk later about how we develop the model. And then a little over around 220,000 total customer connections. So a lot of connections as we're developing demands and loading demands. So with their system, so some kind of unique challenges and unique opportunities with this project is the district didn't have an existing full-scale system hydraulic model. They had always done modeling in chunks, little tiny bits and pieces here and there, but never one comprehensive full-scale model. And they hadn't done a substantial master plan in over 20 years. So no model, no master plan. So really kind of a unique opportunity to help them get moving in the right direction. They did have a pretty substantial GIS database. It was built for microstation CAD conversion. So we ran into some of these CAD challenges with network connectivity and other things trying to get it ready for the model. And they're currently transitioning to ArcGIS Pro and the utility network model. So we had to keep that in mind as we were going through as well. So as you can imagine, with the GIS, the first step was really to get their GIS in shape so we could start to use it for the hydraulic model. And we really did this as a 2-phased approach. So the first thing we did is we just used some GIS tools, trace tools, some general Esri utilities to kind of at least get us started, because if we just pulled the GIS in day 1 into the model, it just, we were never going to get there. So then once we kind of got ourselves in a manner or at a state where we were comfortable building the model, then we built the model and then used the InfoWater Pro tools. Most of you are probably familiar with these, the locate fixed nodes in close proximity, the pipe split candidates, and the crossing and intersecting pipes. And then that really gave us a second set of exceptions or errors to turn back to them. So really 2-phase approach, one in GIS, an initial set of errors, then pull it into the model and use InfoWater Pro to identify those kind of secondary or more model-specific errors. And with the 2 together, we were able to get the model built. So the database reconciliation. So we really had some challenges here with just the volume of data, because they have considerable amount of data. It's a large system, but also, as I mentioned, the microstation CAD conversion. There's always issues with CAD conversion and trying to pull that into hydraulic models. So we found kind of some general issues, just things that they necessarily weren't thinking about in terms of hydraulic modeling. Most significantly, they didn't have any treatment plant facilities. Pump stations were a single point, but they have a combination, which I'll talk about later, of variable speed pumps and constant speed pumps in single stations. So we needed to be able to represent those separately. So, we had to develop a strategy to move away from that. And then we had some issues with storage nodes where they either weren't all represented in the GIS, or they were represented, maybe you've seen before, as a polygon as opposed to a point. So something that the model is fine for GIS, but the model isn't necessarily going to like. So the first reconciliation we went through with the GIS, we found a significant amount of network issues. So pipe splits were probably the most significant challenge that we had. Is when we ran it through the initial geometric network just to look at where we had disconnects, we designated about 70,000 locations where pipes needed to be split. So that's a significant number and a significant amount of effort. There were about 1,000 pipelines just because of the way the CAD was converted, with lengths of less than a foot. Sometimes we're talking about inches, like 1/10 of a foot or 1/2 of a foot, with overlapping segments. They called these drawbacks. So we had a lot of those. And then system valves, some were connected to the system and pipes were split as system valves, and some were not. And kind of a key point to this is just with the number of pipelines that they had, is we were trying to basically split the minimum amount of pipes as possible. So we decided that we wanted to split our pipes only at zone isolation valves or PRVs or critical valves. So that helped us out, not only with the GIS reconciliation, but also with the number of pipes in the model, which ended up, as you'll see in a few slides, of over 100,000. So over on the right, I'm just showing what we basically did, where we took their GIS features and we mapped those to some type of hydraulic model element, and basically did a little GIS gap analysis for them and recommended all these different fixes, how the data should be structured, and we added some attributes specific for modeling. And this was about a 6 to 8 month process, working with them, going back and forth a few times with their GIS group, and getting the data into the right format. So a few more issues that we had once we kind of got to the point where now we're ready to pull into the model, is now we started to have some InfoWater Pro specific issues. And this one's pretty common. Many of you have probably seen this, but flow direction around your nonlinear facilities like valves and pumps needs to be correct in terms of digitization direction. This is a common one that's missed. EPAnet doesn't like when there's either 2 pipes going in or 2 pipes going out. As you can see right here, this is kind of the incorrect pipe direction, where we've got a system valve and we have a pipeline heading in from each side, and EPAnet will basically kick that out. Another thing we found that was really significant was there was no unique identifier on facilities. And this is important as well, is it has to be unique not only within the data set. All pipelines have to have a unique ID, but you can't have a pipeline with an ID of 1 and then a junction node or a valve as an ID of 1, or that'll get kicked out. So we worked with them to try to get this unique identifier, so we didn't have either duplicate IDs, either within the data sets or across data sets. So then again, I already mentioned the gap analysis memo. So we had 11 major gaps and recommendations for them, and then we had kind of a database design where we recommended some additional attributes for them, incorporation into their GIS, just to make it easier for them to update and do that synchronization in the future. So again, I said, 6 to 8 months and multiple go-arounds. I think we probably did 4 or 5 back and forths. with our GIS QC process, pulling it into the model, and then again kicking out exceptions. So the nice thing is, it seemed very overwhelming at first. Like I said, 70,000 pipe splits, but every time we went back and forth, we got significantly smaller number of exceptions. 70,000 became a handful, and then became one or two, and then finally we got there about 5 or 6 go rounds. So finally we're ready to build the model and get into the good stuff. So what we decided to do was in InfoWater Pro use the GIS gateway, where you can actually build these GIS exchange clusters, as I'm showing here in the upper right, where we have some type of ID where we pump pipe junctions, pumps, takes, and valves. And then the nice thing about the GIS gateway is then you can take this a step further and start to map from their GIS database into the model GIS database and do more of a synchronization as opposed to like an import-export. So we were able to build the GIS gateway and build the hydraulic model and successfully finally get the entire model built. So then the next step for us was, we've got a lot of data. They didn't necessarily know where all their zone isolation valves were. They gave us a pretty comprehensive list for us to start out with. So what we started with was what I call a zone isolation run. So this is a low flow, low head loss. So usually we just make our C factors high and run just a really low flow through the system just so we can get our PRVs activated. And when we do that, what we see is with that very low flow and low head loss is you can actually get like a uniform hydraulic grade line across your entire pressure zone. So this is kind of nice because you'll be able to see where water is sneaking through zones or out of zones. Maybe you're missing an isolation valve, or you're missing something else that's isolating that system. And we were able to identify a handful of isolation valves or areas where the system should have been isolated, but the model was telling us that it's not isolated. So this is really nice because if you just start the pressure zone manager, my last bullet here, it's a really good zone validation tool, but I think if you're starting from scratch and starting with the pressure zone manager, sometimes it can't necessarily tell you where that water's sneaking through. So if you start with this isolation run and at least get yourself close, then you can flip over to that PZM at the end, and it's a great zone validation tool. And then you should have, if everything goes right, these perfectly isolated zones. So that's just a quick snapshot of the pressure zone manager down at the bottom here. And I think we ended up with about 11 total zones for there. There are 3 major zones, they're minor zones, and then we had some other zones around the treatment plant that we were able to identify. So one little tip here with the GIS gateway, and I've used this quite a bit, is typically this is going to get set up on some type of machine that's not at the client site. So a lot of times you'll set this up on your local machine or a local server, and you can actually dig into the GIS gateway database. There's a DBF sitting there in the IWDB folder, and I've done this quite a bit. And if you follow the same general GIS structure in terms of the database name and then the the SQL queries and the facility mapping, then all you have to do basically is take this GIS gateway DBF and basically get rid of the path pointing to your machine and replace that with the client's path, copy that all the way down, and then the next time you initialize the model, that will point to their GIS data instead of yours. So that's a good little trick to use. It saves you from going into the going to the client site and then double clicking on all of those different GIS exchange clusters and repointing to the database and kind of resetting all that up. So a little time saver there. So after a few go rounds and some QC, we finally had the model built, and this is what we ended up with. So a pretty large InfoWater Pro model, pretty significant. So we ended up with a little over 100,000 pipelines. 90,000 or so nodes, total junction of over 90,000, 10 tanks, 3 reservoirs, those are our treatment plants, 89 pumps in those pump stations, as I was talking about. And then we ended up with a little less than 500 total valves. So even though they have, gosh, probably 40,000 valves, system valves in their system, we only physically modeled about 500 of those. So those were PRVs, flow control valves, and zone isolation valves. So now we've got the model built. What's the next step? So the next step for us was model loading, and again, just due to the sheer volume of data that we were dealing with, everything was a little bit challenging here. We had 220,000 customer accounts. The nice thing about their data, the way that it was set up, was they had a service lateral and a service point. So we were able to use GIS trace functionality to go from the point to the service lateral to the pipeline. So we were able to build that in GIS, that pipeline to model ID, pipeline ID link that the demand allocator likes. So then we use the demand allocator to load this at the end, and this took quite a bit of time with that many customer accounts. So that was a push the button and wait, either do it overnight or go get a cup of coffee or something and wait for that to kind of chug through. So what we ended up with, what I'm showing here on the right, the way we ended up parsing their demands out was residential, commercial, industrial. They have some data centers. We had a place for non-revenue water, and then individual patterns for each of those. The residentials and the commercials and obviously the data centers all have different demand patterns. So again, just a little useful trick. When you're dealing with that many demands or that many different fields, it's useful sometimes. I don't know how many times I've gotten a model, there's demand 1 through 10, and I have no idea what those mean. Is you can go into, many of you probably know this, but in the DB editor, if you go to view fields, you can right click and go to the field properties. You can actually go in and put in a display alias on all of the default Innovyze field names. So we've all seen demand 1, pattern 1, demand 2, pattern 2, but then you can go and give them something, a meaning, so when you come in later, it will mean something to you, or deliver it to the client, and they'll know what's going on. And that's how I got those to say residential pattern in the screen before. So again, just a quick little tip. So now what I want to do is go into some of the patterns, and the reason I want to talk about patterns is just because MUD has somewhat of a unique system, not only with the closed pressure zones, but also with their peaking factors. And we see this in the Midwest quite a bit, where we have residential irrigation, and it seems like they're always set up on a Monday, Wednesday, Friday schedule. So everyone's just has this significant peak in the morning on the max day when all these sprinklers are coming on, and then it kind of subsides and you get that normal diurnal pattern. The other interesting thing here is their 3 zones act so differently, just simply because zone 1 here is a primarily non-residential zone with commercial and industrial, so it kind of comes up in the morning and subsides in the afternoon with that kind of midday peak that you'd expect. And then as we move to zone 2, it's kind of more mixed, so you can start to see this residential irrigation influence in the morning, and then kind of comes down and you get that secondary normal diurnal pattern. And then as we move out to zone 3, that becomes more of a primarily residential and less commercial and industrial influence zone. So this is kind of your typical, what we see out here is just this huge peak in the morning, which really dwarfs the evening afternoon diurnal peak. So with MUD's system, there's a challenge with, they have a very high peak hour factor. So we're talking about 5, 6, sometimes even 7. So it it became challenging when we moved into calibration and just in analysis sometimes too, is their system performs very, very well on the average day and even the maximum day. And they have just this kind of 3-hour window, you know, between 4 a.m. and 9 a.m. every morning. That's the peak hour is really significant. It's a challenge to get through, and then it kind of subsides and goes back to normal operations. So really, their system is really designed to kind of react and meet this peak in the morning. So with peak factors, now we move into model calibration. And this was pretty interesting too, a pretty substantial calibration effort, just simply because of the size and the scope of the model. So we ended up with 30 flow tests across those pressure zones. And within those, we had residual hydrants and flow hydrants. So a total of about 87 hydrants in total. We did this over a period of 3 days. And then what we did is we brought all that data back in-house and started to use the InfoWater Pro calibrator to adjust C factors. And we had to make some adjustments and take a little bit of a different approach here, just simply because, again, the geographic scope of the model and also just the way that their system reacts. So what we ended up doing with calibration groups is we had our typical age of material, which you know was pretty well populated in their GIS, and then we split out distribution and transmission. So we'd have a transmission calibration group that we were assigning different C factors for transmission systems than we did for the distribution system. And that was an iterative process. We had to go through that a couple times, obviously, because the transmission C factors are affecting the entire zone, whereas the distribution was only affecting certain areas of the zone. And that's another thing that we had to do, is simply because you can see in zone 2, this hydrant test 24 is so far away from, you know, hydrant test, you know, 7 or 8 over here, that we had to come up with these zones of influence, and we just came up with, you know, I think we used like a couple of miles. So, you know, when we were adjusting for 24, we only kind of let the C factors adjust in this area. We didn't let, you know, the whole zone, because we never would have got there. So that was a little bit of a nuance there with their calibration. And, you know, after a few iterations, we were able to get there. And then I just want to chat briefly about some challenges that we have with calibration. So the first one was for not only EPS calibration, but also just for, you know, regular fire flow calibration, is there's MED system. They really don't have a standard operating procedure for how they operate their system or any automation for controls. So that, you know, presented some challenges for us, obviously, because, you know, we did have SCADA data, but we didn't really know what was on or what was off during certain time periods, and became more challenging with the EPS because, you know, it's more of a reactive system. So we didn't know, you know, when our tanks kicking, when our pump station's kicking on, when are they kicking off. The other thing is, with that large of a system and with no automation, is sometimes we think the flow duration wasn't long enough to allow the system to basically react. So we didn't know whether we were seeing losses because it was true, you know, head loss through the pipelines, or whether they were losses just because, you know, by the time the operator at system control saw the pressure drop and was able to kick on pumps, if that lag just was too much or wasn't correct. And again, the large area presented challenges. You know, the first time we went through, we tried to do it kind of on a zone wide, and obviously that didn't work. So we had to go back and kind of modify our approach, as I said. And then this one is really interesting. So we got through zone 1, that one went pretty well. And when we went into zone 2, which is that first large closed pressure zone, we just went round and round and round and kind of spent a lot of time, and it just couldn't work, and we could not get it to work. And finally, we just had some kind of got some senior people involved, some kind of surge people here at HDR, and some other operational people, and they looked at the system and they just said that there's no way that something must have happened. They had to do something to adjust their system with these closed systems. with all these different, like for example, zone 2 had 12 large constant speed pump stations pumping into the zone. So we went back to the client and said, was there anything done, or have you done anything to adjust? And they said, oh yeah, and lo and behold, they went around and trimmed the impellers on basically every pump in every pump station to kind of get the system to work. So, that obviously, threw a monkey wrench into the calibration. So we had to go back and kind of do some, more pump tests, look at SCADA information and see if we could adjust these pump curves to try to figure out what was going on. The other thing we found is, to the best of our effort in GIS to get the PRVs and pump stations modeled in the correct direction of flow, we found that we just missed a few. So, the good thing about the calibration is we were able to find those, and we found, I think, 2 or 3 PRVs that were modeled backwards. We're able to get those corrected. So the calibration was really good for 2 things. One is it helped fix some facility issues for them, but it also, obviously got us a C-factor calibration. So finally, the results. And this is interesting just because, as you would expect, in zone 1, which was the gravity system where the pumps were reacting closer to what they were originally designed and manufactured for, we were able to get some really good calibration. This is the AWWA, within 10 feet of HGL, is kind of in that acceptable range. 5 feet is desirable, and then moving down, 2 and 1. At the planning level, we wouldn't expect much to be, down in the 2 foot or 1 foot range, especially with some of the challenges. But you can see, on zone 1, we had statics. We were able to match pretty much everything. Residuals and pressure drops, 90%, 82%. So not too bad. But then as we move out into the closed zones with the impeller trims and the modifications and some of the changes, you can see this starts to drop down. Still able to get okay within 10 feet, but then, we're only hitting 60% in the 5 foot range. And then as we move further away from the gravity zone, as you would expect, this was the most challenging because now we're two times removed from, we have all these different uncertainties in zone 2, and then that is exacerbated when we get to zone 3 with another closed system, more impeller trims, is we were down kind of in the less than 50% range for within 5 feet. And then we did some regression analysis for them. So for the straight pressure comparison, you can see we're not doing too bad, an R squared of about 96%, 0.96. And then when we do the pressure drop, that obviously, with all of those different inaccuracies and uncertainties, that starts to drop out. We get some outliers, and we're down to 0.87. So overall, not too bad considering the level of data that we had, the scope of the model, and some of the challenges and inaccuracies that we had. So we were happy with this calibration, and we actually went in post model. We're doing a master plan for them right now, and did some more specific sensitivity analysis, and ended up adjusting C factors a little bit more for the master plan. So also, as I mentioned, EPS analysis, we were able to match somewhat well with their tank levels, but again, with no standard operating procedure, it was a little bit challenging for us. We almost had a little bit of too much flexibility or too much rope to play with controls to get it to match. So really the best we could do is over the calibration period that we selected, which was the maximum day, we just had to kind of bake in some controls to get tank levels to roughly match, and pressures as well. So this is another one with tank levels. You can see, we're not matching perfectly, but we're getting pretty close. So overall, we were happy with the C factor and then the EPS calibration. Coming down to the end here. So what are the next steps and lessons learned for us? So for MUD, the next step was now that they have this model and haven't done a master plan for some time, is let's roll this right into a master plan. So we took the model and we're currently working on a system-wide water system master plan for them. Continuous improvement of the model is important. So, you know, this was our first model in forever. So basically it's a first cut. We don't expect it to be perfect the first time. So as we get more pump information, more pump tests, more facilities, then we can continue to improve the model. And the GIS Gateway really helps us do that, just because it's more of a synchronization process opposed to that import-export process. And one little anecdote here, as we were going through the master plan, developing the CIP, we were basically recommending some transmission projects in a certain area, and it got them to scratching their heads. They didn't understand it, so they went back into their GIS, and we actually found a critical piece of missing main, 24-inch, that they just didn't have in their GIS, so it never got into the model. So they went back and fixed that. We resynchronized and reran, and a lot of those projects went away. So that's what I'm talking about with continuous improvement. We expect to find things as we go through, and then we can continue to get those rectified. I think one of the biggest things on this next point here that we can use the model for is, as we all dive into the model, we're learning and the model is learning, and we think it can help them develop a standard operating procedure. The model's helping us understand kind of which pumps should be prioritized for certain zones and which of these pumps are fighting with each other. You can kind of go in and see, you know, through the model output, the simulation output results, kind of which facilities are fighting with each other. So it's really helping us in the master plan point them in the right direction of, you should really be operating these pumps as a priority, and we should really think about, you know, VFDs in these areas, and it'll help you in the long run. And then just kind of the overall lesson learned. This is the largest model by far that I've ever personally worked on in InfoWater. Everything you add has runtime issues. So if you can avoid reducing pipelines as much as possible. Our first go around, we went in there and we put all the hydrants in particular. I know a lot of times clients want all the hydrants in their models, but I think I'm starting to lean towards, you know, talking them out of that and just modeling the distribution system's ability to deliver to a hydrant, as opposed to modeling each and every hydrant, and, you know, just saves a significant amount of runtime. So those are kind of the next steps, lessons learned for us. And then on the next slide, I just wanted to chat a little bit about InfoWater Pro in general. So this was an exciting project for us, because right as we started, InfoWater Pro had just come out, and the district was already talking about ArcGIS Pro and transitioning over. So we decided to use Pro on this project, and we were early adopters, probably one of the first clients and, you know, one of the first users of Pro. So we were able to identify, you know, admittedly when Pro first came out, there were some inconsistencies, some bugs. So we were able to, you know, identify a lot of those, and the product has significantly matured. So I think just, you know, in a year or so time frame, we've seen leaps and bounds of InfoWater Pro improvements, and the product's really a stable product right now. Speed is a significant advantage, especially when you're talking about, you know, 100,000 plus pipes. And after I get off of this slide, I'm actually going to show you a live demo and just pan around InfoWater versus Pro, and you'll see right off the bat that the interface is significantly faster. And then I personally just like the ribbon interface. I think it's a little bit more efficient, you know, when you're dealing with, you know, a lot of different commands, just being able to, you know, access those ribbons, or even have the quick ribbon at the very top. So I think just the Pro interface itself has some advantages. I personally like it a little bit better than the old, you know, the old interface of our GIS. So with that, I will just roll into a little bit of a demo here. And the first thing I'm going to show you is, this is the entire MUD system model, and this is InfoWater. So this is the old ArcGIS. And what I'll do is I'll zoom in here, and you can see, you know, I've kind of got a lag, and I've got a wait here, and this will eventually catch up. eventually, I hope. I've noticed that if you have a background like I do in this case, and I like backgrounds in my model, is it seems to significantly slow down the ArcGIS ArcMap. And then, if we zoom around, again, we've kind of got to wait a little bit for it to catch up. And then this is probably where you can see it the most. If I zoom out, it kind of goes through, and you've got kind of this chug, chug, chug as it goes through and finds the whole model. So now what I want to do is let's switch to Pro. This is the same model in Pro, and I'll just zoom in, and I think you can see kind of right off the bat, there's a significant, it still has to catch up, but it's considerably quicker. And then, zooming around, panning around, and then here's where I think you'll see the most significant difference is once I go to the zoom layer. See that's almost instantaneous. So a significant advantage there, and especially when you're talking about 100,000 pipe model and you're in here for 4 8 hours a day kind of doing modeling, is for you to sit there and wait 5-10 seconds every time you zoom or pan around versus having to be almost instantaneous. I think you can kind of see the advantages there, and for us it definitely was an advantage. So with that, I think that brings me to the end of my presentation. That's my contact information there, so you can feel free to reach out to me. And then, I don't know, were there any questions, Tim, as I was rambling on?
I think there were a couple questions from Mickey, and actually, Scott, if you wouldn't mind just advancing one more slide. I think we've got everyone's contact information on that next one.
Sure.
Yeah, perfect. So that's all our speakers' contact information there on that last slide. I think maybe you might just follow up with Mickey here later because he had a couple different questions, but one was, Scott, were those changes, cleanups in the model, build-up process ever brought back to GIS so that you don't have to do that again in the future? So when you were doing the GIS cleanup, that was done in the actual GIS, right? Or was it just done within InfoWater, I guess?
Oh yeah, I should have made that clear. So that's a really good point and great question. So we specifically designed this to be a GIS integration project. So we were trying to do as little as possible in the hydraulic model. So our approach basically was to identify the issues in GIS, turn those back to the GIS team for MUD. They would make those fixes. They would give us a new cut of the GIS, and then we would pull it in and do it again. So if we found an issue, we didn't do it in the model. We basically identified it, sent them back a memo, and then would pull it back in. And that's what we're doing moving forward, is they're continuing along the lines of adding new facilities, and then every 6 months or so, or periodically we'll get a fresh copy and we'll synchronize that. So yes, for that GIS integration to really take hold, you want to do as little model manipulation as possible.
Yeah, that's perfect. We advise the same thing, and then our implementation services here at Invise find the change with InfoWater's special tools to find those hydraulic connections that are not always found in raw GIS, but make the change in the kind of database of record GIS.
Exactly.
Perfect. Well, I want to be respectful of everybody's time. We've gone a few minutes over here. Thank you to our presenters. That was an action-packed couple of hours. Hope everyone really appreciate all the technical expertise we really had over the last couple hours, looking at asset management solutions, drainage solutions from University of Oklahoma, Andrea, and then distribution modeling as well here from Scott. Really great, really showcases the breadth of kind of the Invise community. And we will have kind of a landing page after all of this where we'll have recordings of the presentations and kind of summaries of each as well. Thank you to the presenters for allowing that. And again, we'll have one more Water Talks presentation next week on Tuesday, same time. But after that, we'll see you all in 2022. Thank you all again. Thank you, Scott. Thanks to all our other presenters still on the line. And yeah, have a good rest of your day, afternoon.
All right, good. Thanks.